Hi, this is Dr. Bay and Bugsy, and today we're going to talk about a quantitative approach to understanding acids and bases. We'll delve into Bronsted-Lowry acids and bases, as well as how to predict equilibrium shifts using pKa values. Stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
The definition of Bronsted-Lowry acids and bases is based on the transfer of a proton. An acid is defined as a proton donor, while a base is defined as a proton acceptor. Let's take a look at the following acid-base reaction of hydrochloric acid reacting with water. Hydrochloric acid is donating its proton to water, and water is accepting the proton. The products of a proton transfer reaction are called the conjugate base and the conjugate acid. How this happens is that one of the lone pair of electrons from water, highlighted in green, is forming a new bond to the green hydrogen of HCl, and the purple bond from HCl is breaking to form a new lone pair of electrons onto the chloride ion. What is occurring is called a reaction mechanism. It's a step-by-step description of a reaction to show which bonds are being broken, which bonds are being formed, and in what order the bond changes occur. To show the movement of electrons, we use curved arrows going from the electron source, often where a negative charge is, towards an electron sink, often where a positive charge is. One way to predict when proton transfer reactions will occur is by a quantitative approach of comparing pKa values. A reaction reaches equilibrium when there is no longer an observable change in the concentrations of reactants and products. At equilibrium, the rate of the forward reaction is exactly equivalent to the rate of the reverse reaction, which is indicated with two arrows pointing in opposite directions. The position of equilibrium is described with the term KEQ, which is the equilibrium constant. KEQ can be defined as the concentration of products divided by the concentration of reactants. So for this example, the products are A- and H3O+, while the reactants are HA and H2O. However, when an acid-base reaction is carried out in dilute aqueous solutions, the concentration of water stays constant, so we can actually remove it from the equation. This gives us a new term, Ka, which is the acid ionization constant. Basically, Ka measures the strength of the acid. The larger the Ka value, the stronger the acid. Ka values are often either very small numbers or humongous numbers. So for convenience, chemists often use pKa values, where pKa equals the negative log of Ka. The lower the pKa value, the stronger the acid. One pKa unit is equal to 10 times the change in acidity. Here's a list of pKa values of common compounds that you'll see in this course. Feel free to either take a screenshot and save it as a picture that you could reference for the remainder of the course. Now, let's look at some examples where we use pKa values to compare acidity of various molecules. For each pair of compounds, identify the more acidic compound. In example 1, we're comparing phenol versus water. If we refer back to the pKa chart from the last slide, we'll find that phenol has a pKa of 9.9, while water has a pKa of 15.7. Since phenol has a lower pKa value, phenol is more acidic than water. In example 2, we're comparing hydronium ion versus hydrochloric acid. The hydronium ion has a pKa of -1.8, while HCl has a pKa of -7. So since HCl has a lower pKa value, HCl is more acidic than H3O+. Now let's use pKa values to compare basicity. In example number 3, identify which of the following anions is a stronger base. To do this, we'll have to look at their corresponding conjugate acids for each base and determine their pKa values. For ethine on the left, its pKa is 25, and for ethane, its pKa is 50. Of the two values, ethine's pKa is lower, which means it's a stronger conjugate acid than ethane. The stronger conjugate acid generates a weaker base, and the weaker conjugate acid generates a stronger base, which means of the two anions, the molecule on the right is a stronger base. Lastly, we're going to use pKa values to predict the position of equilibrium. One thing to remember is that equilibrium will favor the formation of the weaker acid, meaning the acid with a higher pKa value. To do this, first we should identify the acid on each side of the equilibrium. So if you're given the acid and base, remember that the base is the proton acceptor and the acid is the proton donor, which will form your products a conjugate base and a conjugate acid. So on the left side, the acid would be HCl, and on the right side, the acid would be the hydronium ion. Second, we'll compare their pKa values. HCl has a pKa of -7, while H3O+ has a pKa of -1.8. Since -1.8 is higher than -7, equilibrium will favor the right side. So in summary, Bronsted-Lowry acids and bases are proton transfer reactions that produce a conjugate acid and a conjugate base. Reaction mechanisms use curved arrows to show the flow of electrons, and we use Ka rather than Keq values for acid-base reactions where pKa equals the negative log of Ka. And two important trends to remember are that the lower the pKa values equals a stronger acid, and equilibrium always favors the formation of the weaker acid.
Organic.